Hello. Hello. Sorry. Hello. Yeah, that's okay. Yeah. Okay. Okay, so welcome to the last session of the day. Vikraman is going to continue talking about category theory for semantics.
Yep. Hello.
By the way.
Hi. Okay. Right. So we've been talking about logic and process, and right. So it's no. So right. So we've looked at logic and so logic. I want to go to and no, it's just the Curry-Howard correspondence. Okay, so the thing we all know is that there's the logic theory. There is a correspondence between proofs, propositions, I times A proofs. And nothing here. But oh, sorry. Yeah. Right. Okay. So.
Probably take a deep camera and project it on the back screen.
Here and equations.
Sorry, Jim, but I bet there's a pen with better contrast.
Right. Yeah. Okay. Okay, so there is a Curry-Howard correspondence that we all know about. Informally, it says that propositions in logic can be treated as types, and proofs can be treated as programs. And in logic, we don't distinguish between two proofs of the same proposition, but in programming languages, we talk about equations on programs, like the beta, eta equations. So this Curry-Howard correspondence can be extended to a Lambeck-Ruthier correspondence where you analyze this whole thing using categories. So as it turns out, these structures we've been studying, the Heiting semilattices, these are special kinds of categories, and the propositions correspond to objects. And oh yeah, this is just right. Green, red. Okay. Yes. No, not good. Okay. And programs are arrows, but these are a better way of saying is these are generalized elements. Because we can talk about open terms and closed terms. So generally, when you think about open terms in an empty context, these are just elements. So one arrow A, where you can talk about, closed terms, and then you can talk about open terms, and these are terms which are varying over a context gamma, right? So generalized elements. And then equations become equalities or coherence diagrams. Okay? Yes, so both logic and type theory can be interpreted in categories, but categories where we don't distinguish between arrows, these are just posets. So when we say P is less than or equal to Q, so there is at most one arrow between two objects, P and Q. But in a general category, we can have so a poset P has less than or equal to, but a category has a Hom set between objects P and Q, which is a set. So I'm assuming that my category has Hom sets, which means the Homs are sets, so they can have multiple elements. And given a category C, you can always forget the thing. So you can turn a category into a poset by truncating it, right? So you say that so given two objects, you can say that P is less than Q if and only if there is an element in this set. So there's a way of truncating categories to posets, and that's one way of thinking about the Curry-Howard correspondence, that you're moving between posets and categories. And, so we have for intuitionistic propositional logic, we have these posets plus top int implication. When we take the corresponding logic, we get simply typed lambda calculus, and so these posets, we actually want to study them as categories now, and as categories, they are exactly CCCs, so Cartesian closed categories, and we've seen them, multiple times in different things. So Cartesian means it has 1 and times. So the top now 1, this is times, and closed means it has these exponentials. So right. So the first thing I'm going to define is Cartesian closed categories, but in 3 different ways. Okay. So generally, if you go to a category theory textbook, it will say, so definition 1, a C is a category with a terminal object, binary products, and exponentials. And the way these are usually defined is it's the limit of the empty diagram, which is how Chris defined it in the category theory lecture. And this is a limit of the discrete diagram with 2 dots. And exponential objects, well, the very low-level definition that you would often see is for all f in this category C from So I'll write f is a object of the Hom set of C from z times x to y. There exists a unique arrow, which I will, because it's unique. So there are different ways of writing it. Some people write lambda f's, or you can write it as f sharp because it's the currying to the right, which goes from the z to x times y. So y to the x. So y to the x is the exponential of y is the exponentiating object, and x is being exponentiated. So exponential of x by y. I think I got it right. Okay, and such that so it's the unique f sharp such that if you go from z times x to y, then you can also apply f sharp times 1x, go y to the x times x, and it comes with a evaluation operation parameterized by x and y, which takes pairs of exponential objects and an object of type x and evaluates the thing to y. Okay, so this is one way of defining it. This is but as a type theorist, I like adjunctions. So if you like logic and type theory, you should really be looking for adjunctions everywhere. And all three of these things can be turned into adjunctions. Okay, so definition 2, C is a category such that. So yeah, so this is kind of like the things that Jules was saying about Markov categories having copy and delete. So inside a category you can drop, right? So cat is a category, right? And inside cat I can write a functor from any category C to the terminal category, right? So it just goes to the terminal, and then I can copy. So I can write this to C times C. So from a category C to the product with itself, I just take objects and duplicate them, and I take morphisms and compose them in parallel. So that's my diagonal functor. Okay, and the third one says for all A in C, blank times A. So if I have a diagonal functor like this with the right adjoint, so let me complete the definition. So C to C have right adjoints. Okay, so what does this mean? This is a way of rephrasing this whole thing, but in a more type theoretic way. So I'm saying that there's a canonical way of going from C to the terminal category, but there's a way of coming back. And because it's a terminal category, if I want to come back, I have to pick an object in C. Okay, so the right adjoint to this is going to tell me, okay, you have to pick an adjoint in C, and there's one object in this. So let's say this. So C must have an object which is going to be the image of the right adjoint. Okay, and the right adjoint condition, if you unpack it, is going to say that C gamma 1. So for any object gamma in C, this thing should be isomorphic to the singleton set. Okay, It requires a little bit of work to see this. To know if it's clear. I don't know if we covered junctions in detail. Okay. Let's see what it does for the second thing. Okay, so the first one. Okay, so C to C times C needs to have a right adjoint. So given pairs of objects in C, I have to produce an object in, pairs of objects in C, I have to produce another object in C, and it has to be right adjoint to the copying map. Okay, so the guess is there should be an object like A times B. Okay, and what is the right adjoint going to say? So C times C from gamma and okay, you have to unpack the right adjoint definition to see this, and this should be like C of gamma comma A times C of gamma comma B. So having products in terms of Hom sets says that there's a way, if you have a map from gamma to A times B, you can turn it into a map, into a pair of maps from gamma to A, gamma to B. Okay. Okay. I think this should be gamma times gamma.
That would be parenthesized C cross B.
Yeah, so these should be tuples. Right, and this says, yep. No, we're saying that there must be a way of assigning.
For the right element, I read that the concept gamma is A cross B.
Yeah, so there is an object A cross B, which is what the right adjoint is giving me. Okay, so I mean, maybe it's worth expanding it out properly, but at the end, what you'll get is this Hom set isomorphism. Okay, so just to, if you don't remember adjoints, so C and G. So D X G Y. Okay, and in this situation, we want C. This is diagonal minus C, and we're trying to find G, which is right adjoint. So G has to take a pair of objects and return an object in C. So let's say for every pair of objects A and B, there should be a G A comma B. And I'm writing that as G A comma B. Okay, and if you expand out the thing like this, you should get this exact thing. Yeah. Okay, and that is the type constructor for product. Okay, and then for exponentials, it's parameterized by a object A. So we can only say that for every object A, there is a way to exponentiate using A, right? So it's saying C gamma times A, comma B should have a right adjoint, and that's going to be the B to be A. Okay. Now, yeah. So definition 1 and definition 2 are equivalent, and that's what you need to check. Essentially, so it's important to maybe write down the map. So when you go from F, you go to F sharp, or in more functional programming notation, you are making a closure with A. You're creating a higher order function A to B in the context gamma, right? And so this is currying, and if you go this way, the map come here, and this is F flat, so that's uncurrying, okay? And you do a round trip, curry, uncurry, you should get back the same function. Okay, so, right. And now the reason I'm interested in definition 2 is because I'll give a definition 3, and it's, so I wrote gamma for the objects, and that's very suggestive of context. So gamma to 1 is like a term of the unit type. Okay, so you take this presentation of a Cartesian closed category, and you can write down a type theory for it. Okay, so so C is a CCC if so for every gamma there is an object, let's say star. Okay, and it has to be unique because it's going to be the singleton set. So you say for anything of type unit, it must be equal to star. And that's so this is my one introduction form. It doesn't have an elimination form, and this is my one eta, or so the eta rule for units. Okay. Yeah. Yeah. Sorry. So this. Okay. Yep.
You say it doesn't have an elimination form, but isn't the elimination form given by whatever is that a band up there?
Yeah. But this is not a type former in my category C. So I'm looking at only the things which come back to C. So I mean, you could write an eliminator, of course. I mean, empty. So you could write like let x.
So, but in this case, there's no elimination form because those things are implicitly represented in what you're writing down now. Or?
Okay, so why does it not have an elimination? Because you go from here to here, but there's nothing to do over here, right? So you go from okay, so maybe it'll be clear when I write when I turn this into an eliminator. Okay, so this is saying I want something to go from gamma to A times B, given gamma to A and gamma to B. So given E1, A, and E2, B. Okay, so going from here to here is my introduction, and going from here to the right, from gamma to A times B, I can produce gamma to A, so that's my elimination. Okay, and same thing for second projection, B. Okay, so the map's going left and right, But when it's a unit thing, I don't really have any useful information on the right. So I just say there's no eliminator.
Your implicitly encoding goes up with the back and the skeleton, right?
Oh, right. So the fact that this is 1 is why it's units.
If you have one, you're going to implicitly encode those in the back end.
Yeah.
So is this true? What are the
What are these?
what are differences like can people also?
Okay. Yeah, I'm sort of confusing type theory and category theory notation. So C is a CCC if for every, so if I wrote it in normal, so there is so there exists 1 in C such that for all gamma in C there exists star from gamma to 1, and this star by the eta rule is unique. Okay. The same thing with products, and now you have to encode this isomorphism somehow. So so gamma. So this is the beta and eta for products. So if I have gamma derives E1, E2 type A times B, then gamma derives first on E1 A. That's the beta, and similarly you will get it. Okay, so products come with 2 beta rules. So just let's say beta 1, and then E1, E2, B. Okay. Right. So that's products, and so this was definition 3, right? Okay. So definition 1 should imply definition 2 should imply definition 3, and from 3 you should get 1. So you close the loop. Okay. So it's worth going through it just to check everything. And okay. And so now exponentials are very strange, right? So if I take this adjunction and just turn it into functions, I would get and this is where you kind of need the context, right? Because we're talking about product inside and exponentials on the other side. So so one way of turning this into a typing rule is to just say this, that the introduction for functions is going from top to bottom, and the elimination is going from bottom to top. And then it becomes very easy to write down what the beta eta should be. So comma derives lambda x of E1, E2. Okay, I don't think I'll write this because it's kind of useless, and we need to go to. Okay, so functions have an introduction rule like this, but the right elimination for functions, or how it is usually presented in logic, right? So is E1, E2, B. All right, thank you. And now functions have beta and eta. And now, because we are using terms, we need a way to talk about how these two interact. So what do I want to write? So if I have gamma comma x colon a derives E1 colon b, and if I have gamma derives E2 colon a, then gamma derives lambda x dot E1 applied to E2. And now I need an operation here, which will actually allow me to curry and apply this E2. So let's just write for now. Okay. And so this is my lambda beta, and the eta rule is okay. So this should be something you see all the time, right? So there needs to be a way to connect it back to the categorical semantics, and let me go back. Okay. So now we seem to be lost in syntax again, right? And So what I want to get, so just like we had, the free heighting semilattice on X, similarly we should have a free CCC on some signature, and this signature now is going to have initialization and a semantics. So just like for logic, we had something like this. We want to replicate a diagram like this, and we want to show that there is a presentation of the simply typed lambda calculus, which exactly presents the free CCC. And we'll say the free CCC on some signature. So a signature has base types, sigma, and constants. Okay. So just like Jules was talking about monadal signatures, this is a signature for Cartesian closed category. Yeah. Oh, yeah.
So my question is that, like, okay, so what you are basically doing is that you have definition in the categorical way, and you're using that to like come up with the.
Yeah, but I didn't give you the full presentation of SPLC yet, because there's issues with substitution, right?
Yeah, my question is simply so the categorical definition I don't understand fully. So
okay.
Comments are so what I understand that you can have rules that typing judgment that you type to terms, and there is also the computational rules that you are defined. Are they separate or like?
Okay. Right. So every so there are types, there are terms, there are equations. When you add a type former, you give a term former and equations. So every type comes with terms and equations.
All right.
That's how I'm presenting it. Yeah. It's not the only way of presenting it, but yeah. Okay. Right.
I have one question.
Yes.
What is the description there with
Yeah, it's V. It's semantics with respect to a interpretation of base types and constants. Okay. Well, I'll keep some of the rules, but so what I want is a principled way of presenting substitution, because I need that to generate the free CCC and give a proper categorical semantics. So I will start with types. So everything I write in this grammar is a valid type. So it's either a base type, or it's the unit type, or it's products or functions. Okay. So anything written in this grammar is a valid type. Yeah. Sorry.
Can you explain what the problem with substitution? In words, you don't have to do that formally.
Yes, the problem with substitution is just there doesn't seem to be a formal construct in the definition of Cartesian closed category which corresponds to substitution. I mean, not by definition. You have to derive it somehow. Yeah, it is composition, but I want to derive it. Like, how does this this thing is how do you get this is what my question is. I mean, it is a composition at the end, but I want to write down a grammar and judgments for it. Okay, so so these are the types, and then we have contexts, right? Okay, and then I have raw terms. So it's all these symbols for the unit and pairs. First. And variables and lambdas. And 2. So I say raw terms because you can write down arbitrary terms, and these might not be typed. And the only semantically meaningful terms should be the ones that are typed. Okay. So I distinguish between raw terms and terms. Okay. And then what's next? Raw terms, and then substitution. So I say what is a valid substitution. I say theta equals this e x. Okay. And what else should I say? Oh, right. Yes, constants. So all the things from tau. And what am I missing? Ah, yes. And now I will fix the judgments. So I prefer to, rather than putting side conditions and things, I prefer to write down judgments for every well-formed thing. So so first I want a membership. Then I want a renaming, and then I want substitutions, and then I want terms. Okay, I think this I want. Right. Okay, and now so these things are valid, but these are kind of obvious. So I will.
So you're not
yeah, so constant. So I'm kind of downplaying a bit, but yeah. So every so these constants they are typed in the base type. So you would just say like so t is a constant. So for every t in tau, the constant will have something in the base type, and you interpret it as it'll be well typed in the empty context. Okay. All right. So now I have these judgments, and I will write down structural rules. Okay. And every structural rule will have a semantic meaning. So so the membership judgment is yes. But I think it will be clear. Yeah. Right. So so x colon a gamma comma x colon a. That's one generator for the membership judgment, and I have x colon a and gamma x colon b. So this is a De Bruijn index for where the x colon a term is in the context, here or there, right? That's what Connor calls it, right? And okay, so on this side I'll write maybe syntax. On the other side I'll turn it into semantics. Okay, and then this judgment says that gamma weakens to delta. So this or go delta. Okay, it has a congruence rule, and here you have an actual. Okay. So yeah, and what has happened? Three rules, and then substitutions have. So the empty substitution, and okay. Right. So so maybe okay.
Just honest that someone wrote up the definition of thinning, then it wasn't me.
Okay. Yeah, I don't. Yeah, right. I don't know what exactly thinning is, but this is. I imagine it's the same thing. Yes. And right. Question. Right.
You were systematically generating the typing rules from the categorical.
Yes, and at some point I gave up and went back to syntax. And I'm trying to go a little bit here, a little bit there, to finally.
There's nothing. Like,
there's really nothing fancy here. The point is, okay, when I give semantics to this, I will construct a category, which is exactly thinning. So for right, so I wrote down some judgments, and and I should say what substitution does to terms, and this is defined by so substitution on variables will do the thing where it's if theta is empty, then it should not be a valid substitution. So the only should be the I, comma for x, then e. Okay, maybe I should do it separately. So substitution on variables and substitution and I x on x is e, and e for y on x is phi. That's phi y. X. Right. Okay. So there is a way of defining it on things. So E1, E2, it's going to be homomorphically on everything which doesn't require binding, blah blah blah. And when it is on binding forms, I will do the semanticists trick, which is to just do I rename x to y to avoid capture, and then I just write theta y for on applied on e. Okay. And so there's an action of substitution on terms, and now I can properly set up my my lemmas, and the lemmas are going to have a syntactic counterpart and a semantic counterpart. So just to make sure, so I'm trying. So now I'm defining. Okay, let me just write. So first, these renamings are going to form a reflexive. So first, so lemmas. Okay. So one. For all, so these are generalized for all gamma, and if go delta, Sorry. Okay. And then say, and then each of these judgments acts on the other in a monotone way. So I want to say if x colon a is in gamma and delta and okay, and similarly the thing. So okay, and right, okay, too many lemmas, but just right. Okay. And the final thing is that this thing that I'm doing is okay. So these are my syntactic substructural lemmas, and each of these things will have a corresponding semantics. So, so I have 5 different judgments, and I want to construct a semantics function, okay, which will take each judgment. So with respect, fix a particular valuation function for base types, and it's going to interpret each judgment in any CCC, okay. Okay, so what do these look like? So the meaning of the membership judgment will be an arrow. So I'm just dropping these. Okay, and so it's a bit. So what do you? So let's just write down a couple. So how you write these things? It's you go so gamma. So right. Okay, I should first define types and things. Okay, so because there's only 10 minutes, so so the meaning of right and types become exactly the homomorphic product thing, right? It's just a change of symbol, and same for the exponents, and the same for contexts. The empty context is the terminal object, and okay, so I've lost my names, but that was intentional, and that's why I keep my membership judgment around. Okay, and then right, and then I give an evaluation on the base types and things. So types and contexts are there, so I can just drop these things. Right? No, they exist, and then so how do I write? So I do induction on this, and I write down a map from gamma to A. So the first rule, it goes from gamma times A, and I use my second projection to go to A. And then this other thing goes gamma times B to right, so gamma times B, and then on top I write, so gamma goes to A is a map like this, okay, times 1B, and then I do A times B, and then I go to A divided by 1. Okay, so this membership judgment, it only uses phi2 and products, right? So it's taking projections out. Then you have the same thing for these renamings or thinnings, and this is a map from gamma to delta. And you do the same kind of thing. So the meaning of this thing is it goes from 1 to 1. There's only one such map. Okay, let's just say ID. And then you go from gamma times A to delta times A, and you interpret gamma times A. And third thing goes gamma times A to delta. And this is first I have to literally drop my thing. Okay, so these three things. So maybe it's interesting to see. So gamma is a product of things. This is a product of things, and these are generated by projections again. Okay, and now I can write substitutions. Okay, substitutions. Okay, I lost the rules, but yeah. So there's the thing, which is interpretation of gamma to delta goes from gamma to delta, and so one of the rules goes from gamma to unit by applying the terminal map, and the other rule wants to go from gamma to delta times A, and you have a way for going from gamma to delta and a way for going from gamma to A. So what you can do is apply the copy map, but I prefer to just write it like this. So so you take the substitution theta, and I have now delta times A. Actually, that was very easy. Okay, so this is the thing. So this is the pairing map. So if I have so given two such maps, I can produce the unique pairing map. Okay, and now all of this is there, and my syntactic lemmas are there, and I can actually show that these substructural rules are semantically well behaved. So each of these syntactic lemmas has a semantics. So there is a semantic version of each lemma. The first one would be that for any gamma, there is a map from gamma to gamma. Okay, so for all gamma, there is a map from gamma to gamma. Okay, and if gamma goes to delta and delta goes to psi, then the semantics of gamma Okay, so every time I do a transitivity step, it becomes a composition in my Cartesian. So in the CCC I'm interpreting, it becomes a diagrammatic composition. The same thing happens for these. So when if x called a gamma, then the semantics of x called a gamma equal to okay, and I think you can guess what keeps happening here. And so these are the semantic rules and semantic versions of the syntactic rules. And the reason I am doing this is because at the end I want to say that you can construct a category, or you consider the semantics of the the renaming judgment, and then your objects will look like products, and your morphisms will be projections. So it gives you the free Cartesian category on your set of base types, and so that's your category of renamings, and then you'll have a category of substitutions, so where the objects are contexts and the morphisms are substitutions. Okay, and finally then you interpret this judgment. So 2 more minutes, let's say. This will give you an arrow from gamma to A, okay? And now you do all this, now it is sound. Now the thing that is difficult to prove, but with these lemmas it becomes easy, is the fact that finally we can reason about our lambda terms by writing down diagrams in my Cartesian closed category. So if I have gamma derives E1 equals E2 colon A, then the 2 arrows okay, and so this is the, let's say, soundness in PCCs, okay? And to check this, you'd have to do an induction on the equational theory. And the place where you would get stuck is the substitution. And if I had more time, I would. So let me just leave this as an exercise. So at least verify the eta rules. So that's where things go kind of difficult. But you can use the renaming and the substitution lemmas and their semantic versions to kind of write it down a bit more conceptually. And so this is soundness, but do we actually get the freeness? Okay, so to get the freeness, I have to first define what is a homomorphism of models from the free CCC to. So I've defined semantics, I've given soundness, so now I want to define the free CCC over sigma tau as the as generated by so objects are types, and hom A comma B is x colon A denotes E colon B up to this beta eta equational theory, and then well, you have to check that this is indeed a CCC where you can write down lambda terms and use the equations to reason. Okay, and this gives you the free CCC, right? Okay, and this, given any CCC, you can use this whole interpretation to extend a sigma tau signature, go to this. The valuation, you can now construct this. And then the final step is, if you had another interpretation, but it agrees on the valuation, you have to show that this is equal to that new interpretation. Okay, that is essentially very trivial once you make sure the equational theory is sound. And what do I want to say? And right. Okay. And yeah, and oh, sure. So, and the final thing was to say what exactly this is a homomorphism of. So it has to strictly preserve the Cartesian closed structure, which means has to preserve products, exponents, and exponentials, and it has to take the evaluation to evaluation, currying to currying, and product projections to product projections, and pairing to pairing. Okay. So there is a lot of work. You can. It really doesn't exist in full detail written up anywhere, and different people have different presentations, but you should do it like this and write down the whole proof, and then finally you'll convince yourself, and you have to do it once, and you'll convince yourself that the SPLC presents the free CCC. And this is a fact I'll use tomorrow to do some interesting semantics. Okay. All right.
How do you